Sequential patterns. Well, from the title, it's already quite clear that we just essentially pick up where we left last week or the last weeks, right? I mean, on pattern mining. But where up to and including last week, we were essentially looking at tables, just tabular data, IID. Every record generated independently, and okay, I mean, what is going on in this data, and either extracting patterns, models of patterns, and the end rules, I mean, all that good stuff. Looking into neural networks too, I mean, that was also nice. Today, we're going to be shifting gears a little bit and start our journey into structured data. Because as nice as tabular data is, or vector representations are, a lot of data is actually temporal in nature, sequential in nature. And well, it's difficult to say even more data, but also a lot of data is actually graph structured or even further structured. What can we do there? Well, quite a few things. So today we're going to go look into sequences, and by intention, I'm going to reuse a number of the concepts you've already seen. So we're going to see MDL again and patterns and whatnot. The main goal is not to sell you on exactly those things. If that happens, I mean, I'm okay with it because I like this topic. But it's particularly to show that simple ideas still apply in complex settings, but complex settings make things more complex. And the shift from tables to sequences may seem like a small one, but as we'll see. So the question of today, how can we discover the key patterns from an event sequence? And then perhaps the right question is, what is an event sequence? An event sequence, or let me actually, no. In a nutshell, this is what we're going to be doing. We have an event sequence, or many of those. As you can see, this is essentially just a sequence of discrete symbols. So it's not a continuous value time series, right? We're staying still in the discrete data side. And what we now would like to get is from such a sequence or a collection of those, what are now the key patterns? So A, B, C, D, A, and the rest is noise, for example. And as you already know now from last week, we can have quite expressive patterned languages, we can have simple, and so on and so forth, right? We'll be building this up. A bit more formally, we have an alphabet, omega, A, B, C, whatever. Those can represent, I mean, if you're more on the NLP side of things, these could be letters, characters. These could be words. These could be entire sentences, paragraph, whatever, right? Fine with me. It could be alarms going off. It's not a made-up example. When I was still postdoc in Antwerp, we actually developed a number of these techniques that I will show you today with the goal of there's a collaboration with a big chemical plant. I mean, Antwerp has a big harbor, lots of chemical industry there. And one of the most, let's say, upsetting experiences in my life was the tour that they gave me of this plant. And at one moment, it was like in some control room, and there was a panel basically as large as this screen with LEDs, I mean, roughly, well, this large. Zoom can also see it, I mean, small, right? This was a graphical depiction of the plant with lots of these LEDs. And every LED, when it lit up, that meant, well, there's an alarm going off. Something was going wrong. And what you would expect, or at least what I expected, is like, look, there's no alarm going off, right? It's all good. Or like blip, like, oh my God. No, this was like all the time alarms were going off. And there were a number of trained professionals staring at the screen with a big red button. It's not actually technically one big red button, but okay, I mean, you can imagine that. And but their job was to see, is it okay? Or is there is shit on fire, right? I mean, that's, and when shit is on fire, okay, then press the button, shut down the entire plant. You don't want to do this for every little blip where something goes a little bit, let's say pressure is a little bit too high. So officially there's an alarm, but okay, now we can adapt. But if, of course, there's a whole cascade of alarms, right? Pressure rises here and then here and then here, and things start to explode and fire and fireworks and whatnot, right? Okay, then you want to shut things down, but not too soon, not too early, because shutting down such a chemical plant has an enormous cost, because it basically means that for 24, 48 or even more hours, the whole plant is shut down, and starting it up again, enormous costs. So you don't want to do this. Yeah, okay, this thingy was calibrated a bit more, a bit too tightly. You don't want that. So the setup hence was, we now have an event sequence of alarms, alarm A, B, C, D, and essentially what we now would like to find in that data were patterns of alarms. First A, and then B, and then C. Everything is fine and dandy, right? So there was just some overpressure and just moves through the system, everything is good. what are now the anomalies? Those are the real alarms, right? That's what they were interested in. You can think of train delays. In the first lecture, I gave an example there. We also analyzed this exactly the same way. So for a particular station or a particular choke point, you can see, I mean, does a train go by, yes or no? And this train can either be, let's say, a small a or a capital A. Small a is everything is fine and dandy. Capital A means delayed. And because, again, choke points, right? One train that is delayed, other trains that should be actually arriving at the time that now the delayed train is blocking the station, they can't come in, they also become delayed. You can find patterns between delayed as well as on time, and so on and so forth, right? Most people think in time series of continuous value data, but there's infinite examples of discrete ones. Okay, so this is the alphabet. Then we have data. Data could either be one very long event sequence, or you could split it into multiple. Let's call them sentences, right? Or sequences. Completely depends on the setting. I like both settings equally much. There are some fundamental differences, and we'll see that in a second. Now, what is now going to be the type of pattern that we're interested in? Essentially, subsequences. But we're not just interested in subsequences themselves here. So just the AB that I have here, this is clearly a subsequence. I want a little bit more expressivity. I want subsequences allowing for gaps, right? And then how many gaps and so on, all very interesting questions. We'll get to that later. We call subsequences allowing for gaps, we call these serial episodes. Just that you know. Good. And serial episodes, they can be of length 2, can be of length 3, they can be of length anything, right? Everything is fine. Good. So, sequential patterns. Data is a sequence. Essentially, a sequential pattern is also just a sequence. And to occur in the data, so like, hey, in this data, I mean, in this sequence, I see a pattern, it's essentially subsequence matching. So in this particular case, we have this, this pattern AB, and it's like, where in this sequence now does it happen? Is it animated? Yes. Okay. For example, here, right, this is one with one gap, and there's another one, AB, and that are essentially the instances of this pattern that I, A, C, B would like to see. I have a formal definition. Essentially, if you now index all the elements in X, then if you can now find a series of indices such that it follows the same symbols as in the pattern, then we have an instance, or an occurrence, as I like to call it, right? Then that window, because a set of indices essentially defines a window in my data, supports the pattern. Just some terminology that we use. Now, like I said earlier, I like these two data models having one long sequence or many sequences equally dearly. Sometimes the one makes sense, sometimes the other makes sense. But they do create a rather different set of possibilities in terms of what is a pattern and how do we count if something happens or not. The old school model, you could say, the standard model, is the per sequence counting. So if you have many sequences and then you have some query pattern, let's say AB, right? We can now check, does AB happen in this sentence, yes or no, right? Just a binary question. And if it's a yes, okay, then the pattern gets a support of +1. And we do this for every sequence and there we're done. Very similar as how we counted support in item set land, right? How often do we see ABC in a transaction? This is also why this is so old school. Now, for a single sequence, that would mean that patterns either have a support of 0 or 1. That doesn't feel quite right, right? It brings us to the second option, window-based support counting. Essentially, over some definition, over some window, we look at the subpart of the sequence. Do we see the pattern there? And then we move the window. And then do we see the pattern there, 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 right? So essentially now the support will be bounded by how many windows we look at. This allows us to now go for both one single sequence, as well as if we have multiple shorter sequences, we can see patterns multiple times. Depends fully on what the application, what you're interested in. In general, this window-based support counting, to me, makes more sense. We should not do this naively, though. We should first ask if there's any questions. Are there any questions? Tim, there is a question.
Yeah, I have a question regarding the definition of the sequence.
Yes.
Because it states that it's like a sequence of sets. And in the examples here, are the sets just
yes.
one with one element?
Yes,
so
exactly.
Yes.
I'm simplifying matters. Good question. So in principle here, like this A, right, is just A, but I could have on top of it, right, basically this you can sort of see as an item set. Or you could see it as x1, x2, x3, x4, right? I mean, you have multiple variates. And then also in the pattern, we could also have an A with on top of it a Q and an R and whatnot, right? And then the pattern is only supported if we see an A, a Q, and an R, and then a B, right? But good question, yes. Okay, yeah, so we should not be naive. Are there any further questions? No? Okay, good, and I continue. So let's do window-based support counting. So a window strict subsequence, nice definition, whatever. Let's see how this works, right? We have our pattern AB, somehow it's currently God-given. How we actually find these things, that comes later. And what we can now do is we take a window, in this case of length 2, length 1, then we would see very few instances of AB, as you can imagine. We start from the first window, and then, yeah, we see AB in this window, right? So, okay, it has now a support of 1. We move the window. No, we don't see AB here. We move it. No, we don't see it here, but up move. We do see AB there. So we upgrade the support to 2. We see it once more here, once more there, and we're done. Okay, great. AB has a support of 4. Makes sense, right? What would happen if I would not use a window length of 2, but of, well, another number? Choose your favorite number. And basically the question is, what could possibly go wrong? And afterwards, I'm willing to answer your question.
So, like, I get the question.
What could possibly go wrong? No, that's my question. You answer that one. Yeah, exactly. So
like, when we increase size of the window, in some case we can interpret it like increase of flexibility.
Yeah.
Otherwise, like we can get overfitting, approach to overfitting, because amount of noise which can be inside the window together with patterns.
Yes. Yeah.
At some moment of increasing the size of the window, maybe.
True. Yeah, you're on the right track, but you're thinking a little bit too far. I'll get to why. I mean, let's see what Patrick has to say. Oh, Bartolome, you're Bartolome, right? I mean, you're Patrick. I mean, that's so sorry. no. So Bartolome. That's sorry. I was just mixing up the name.
So we might count, if I'm saying correctly, we might count one of threads twice because it will be twice in the.
Exactly.
Windows.
Yeah. Only twice.
Or as mentioned, the length of the window minus the size of the pattern.
Exactly. So if we have AB as a pattern, but we have a window size of 10, then if there's a lone AB in just a sea of nothingness, 1, 2, 3, and so on and so forth. So yeah, that's a bit unfortunate. And then next question, okay, what else could possibly go wrong? Yeah, because this goes wrong, when you start to kind of see essentially ghost instances of anything, noise hits you, right? So during the search, so here we already had the pattern, right? We sort of know that this is something we're looking for. But if you're not looking for patterns, and everything gets a very inflated support. Yeah, it's noise, redundancy, spuriousness everywhere, right? So you don't want to do this, right? At least not naively. Oh, okay, I see that I did not remove my clover leaf. So these are slides that I used to teach back in days when I was teaching IRDM. And clover leaves meant, okay, we're now going a little bit deeper, but in TADA we don't go deeper. This is just the level we're at. It's more like the previous stuff. It's like, okay, this was easy. And now it's more interesting. This is useful. So indeed, fixed window length double counting. Minimal windows is a proposal by, well, originally Heikki Manila in 1996 and then refined in the early 2000s by Nikolai Tati. I find it a beautiful concept. Essentially what we say, that if a window in the data supports a pattern, right, and we can now shrink this window by removing some elements from it, either from the beginning or the end, and it still supports the pattern, but it's not a minimal window. So how many shortest, hence minimal windows, are there that support the pattern? And then all of a sudden, actually things become interesting, because here we indeed have an AB, right? That's minimal. This one includes AB, but no, I can prune the D out, right? Even if there would be a B here, you could say, okay, this is still an instance of AB, but I can still prune it and I still have AB, right? So that's pretty neat. All of a sudden, this double counting is gone. And even better, this is still monotone. Just like the fixed window based, this is also monotone. It's a bit more involved to implement this. I mean, this is a fun exercise if it's a rainy or overly hot Sunday afternoon. But yeah. Now, one thing, of course, that we need to keep in mind is, let's call it now the Igor observation. If we allow minimal windows to be of an arbitrary maximum length, yeah, we didn't gain anything, right? I mean, so let's say A is the beginning of the sequence, Z is the end of the sequence. AZ will always have, or basically any pair will still have an occurrence of at least once, right? Unless you set a maximum minimum window size, so a maximum approach. And that is both good for reducing spurious results. It's good for interpretability, because depending on your data, you may or may not want to find very long range dependencies. Sometimes you do, sometimes you don't. And it, of course, will also increase efficiency quite massively, because you don't have to look over such large part of your data time and time and time again. Good. Yeah, so in this particular case, these are the 5 instances of AB that you would now find supporting AB. Final slide on this. Well, again, stolen blatantly from my IRDM days. Even though you don't really know what level-wise search is, because I didn't bother to teach you earlier in the course, essentially simple basic algorithms that we know now for a very long time that are very good at mining all patterns, as long as you have, if you can define a lattice over your pattern space, which is easy, the empty pattern, all the singleton element patterns, all the 2-element patterns, and so on and so forth, right? Can become a very large lattice. That's fine, as long as it's finite and we can walk over this. And if in hand, we also have a monotone or anti-monotone, same thing in the end, just a different direction, measure of well, how good a pattern is. By, well, for example, frequency. If ABCD is frequent, we know that ABC and AB are all frequent. Also means that if now ABCD is not frequent, we don't have to look for ABCDE. There's no way that it can become frequent. Right? That's the main trick of all these mining algorithms. Implemented different ways, very smart data structures and so on and so forth. They are very good at extremely large scale waste generation. As you know, right? Pattern mining is such a great idea, doesn't work. Now the ideal outcome is more something like this. We want the building blocks of the data, right? Small set, you know, right? Pattern set mining, you already are in the know. Frequent pattern mining does not achieve this, you know. What we're now going to be doing, we're now going to see how can we find such a small set of patterns that essentially models your data, because in the end, MDL, MD-SHML, right? It's just a probabilistic model of your data with interpretable ingredients. Those be the patterns. That was what we're going to do. In order to do so, we need 3 main ingredients. We need a score. How good is such a summary? We need to determine, once we have the score, how can we actually describe a given chunk of data using those patterns? Or in other words, how do we actually compute the score? Because the score, we need some statistics. How do we compute the statistics to compute the score, right? And then finally, last but definitely not least, how do we now find good pattern sets? As you can see, I'm walking from knowing more to knowing less. Let's start with the summary itself. This is just a variant of the slim crimp slide that you've already seen. We want to generalize, we want to punish redundancy, we want to punish spurious patterns. Okay, hence MDL, you know what MDL is. We still want an optimal set that generalizes, so we need to compress. This was all intentional for me to skip, right? And just to show that you can transfer these ideas. You're going to see variants of these slides again, either next week or the week after, when we move into graphland. Just really like hit home, very general idea, right? And if you think, okay, MDL, yeah, just replace it with probabilistic modeling. If I would be saying we're going to be probabilistic modeling, we're going to be doing probabilistic modeling, you would shrug, right? Sure, but good. Now, what is now the probabilistic model? That is the question that would then be interesting. In our case, we don't have and specifically, we call it an off-the-shelf probabilistic model. We define it ourselves. That's the power of this approach. Our models look like this, which is quite reminiscent of a model you already know, namely this code table thing. We also called this a code table, but we now have these two columns that are new to you. So this is all pattern and code, fine and dandy, you know what this is. What these here do, we'll see in a minute. Let's start with first showing how to compute, how to score a given model. We have a data sequence here at the top, and I give you a model of just singletons. And I ask you, please describe this data in terms of these singletons. Only one way you can do it. If there's an A, you should say A, and if there's a B, you should say B, and so on and so forth, right? I mean, that's, if you do anything else, you're giving me a different data set. It's not lossless, right? And well, you failed the course of this. Now, once we have such a cover, or what I call here, this is C stands for the cover, and these are the P stands for the patterns. This is the pattern stream, because each of these colorful boxes here essentially represent a code word, and each color is a different code word. How do we determine the length of a code word? Essentially, we count. So it comes down to how often is the code for X used over the number of codes that are used in general that we could encounter. That's a probability. That's basically the probability of encountering X. We take a negative logarithm because Shannon information, base 2, right? Because bits, and that's the length of the optimal code that we could use. Okay, great. Now that means that the length of the entire CP thing is just the sum of, well, each of these individual codes, right? Which we can simplify as just the sum over each code word, length of the code word times how often we use it. Easy peasy. Okay, let's ramp it up. Second code table, slightly more interesting. I don't just give you the singletons. I now also give you two patterns. I give you pattern ABC and pattern DA. And as you see, we also have now different codes with them, gap and non-gap codes. Because if I tell you here be a pattern, a singleton, an A, then, well, unless you didn't really understand what we're doing, there can't be really a gap in this pattern, right? It's like it is clear. If I say there's going to be an A, there's going to be an A, right? In the code, the protocol we're now agreeing, there's no uncertainty anymore. However, whenever I tell you here be DA, okay, then you can write down probably if the first time I say the D, otherwise why would I say it? But you don't know when you'll be allowed, or you should, I should say, write down the A, right? I also need to communicate that to you because we do allow for gaps. If we would not allow for gaps in pattern occurrences, it would be easy. I say DA, you write down D, you write down A, and there we are. But yeah, where's the fun in that? Okay, so I give you now another cover. We have sequence of pattern codes and a sequence of, well, I call this gap code. So this is the gap stream. And how do we decode this? Very simple. We go from left to right. We start reading code from the pattern stream. This is code P. Okay, then we look up what does P stand for? ABC. We can write down the A immediately here. So that's by reading code P, I can write down in this case A. Can we immediately write down the B? Well, we should check. Well, we check in the gap stream where we read, in this case, an exclamation mark. Exclamation mark is a fill code or a non-gap code. Right? So that means that, yes, you can write down the B. Next, can we write down the C? Let's see. No, there's a question mark. It means there's a gap in the pattern. So no, right? What we then do, because we're not allowed to write down the C yet, we go back to the pattern stream, we read the next code, and we proceed just like that. Well, easy and straightforward. And then this way we can just decode the entire thing. I'm not going to walk you through the entire example. Now, I should mention that in this part of the presentation, later I'm going to change this, I do not allow patterns to be nested. So for example, P, and then at one moment there's a gap in P, but and then I read up. I cannot read another, let's say P or another Q or no, only singletons happen in gaps. It's our little secret. We're not going to tell the algorithm. And I will share with you why we don't tell it later. Good. Now, what are the lengths of these codes? We essentially, again, just simply count. However, we should not count over the entire sequence. It's not how many question marks over all symbols, because we can only get a blue question mark in the context of a P. This is where the interleaving also comes in. So hence, how often do we see a blue question mark in the context of a blue P? Same thing for non-gap codes. We have codes, bam, done. So that already gives us now the encoding. We can compute how many bits does it cost to encode a given data set, using, well, a given pattern set and cover of the data. Still two problems to be solved, but that we know. I'm not going to walk you through the details of how to encode the code table, how many bits this costs. Main point is that the intuition will be clear. More patterns, more bits, longer patterns, more bits, and so on and so forth, right? I mean, I can explain you the details, and we're going to use a log binomial here and there. I mean, I have slides for it. I don't think it's that particularly interesting for you at this moment. But assuming that this thing exists, we're just going to optimize this, and there we are. So how can we do so? Second question we need to answer, how can we now describe a sequence given a pattern set? How do we get to this CP and CG, these covers? They're not going to fall out of thin air. So essentially the question is how to cover your string. I love making the joke. I mean, that's at the conference presentation a long time ago. Now there's many valid covers already for one code table. So here on this code table on the right, I mean, I showed you, which one was it again? I think this one is the one that I showed you, right? But this is an equally valid cover of this data using this code table. And as is this one, as is that one. Which one is best? Yeah, it depends, right? It all depends. What does it depend on? It depends on the code lengths. How many bits do each of the boxes cost? What do the code lengths depend on again? Oh yeah, on how often we use them. Shoot, that makes things a little bit tricky. So there are essentially exponentially many covers, and determining which one is optimal, difficult. Basically, it's optimal. It's impossible. So we're going to drop that we're after the optimum, and rather we settle for a good one. And under the observation I just already made, if we fix the cover, then it's trivial to define what are the optimal code lengths. But I basically just gave you the magic, right? That's the previous slides. Now, given optimal code lengths, so if I give you code lengths, be them optimal or not, we can actually find the optimal cover of those code for the data that we can do efficiently using dynamic program, right? Exponential space, but okay, there we are. We can actually find it, I mean, very efficiently. And what we now essentially do, we alternate these steps until convergence. So we start with some not random code lengths. We just essentially use how often do each of these patterns happen in the data at all. Then we do the dynamic programming dance. We then say, okay, where would we use them? Then we get new count and so on. And this converges very quickly. Typically in one, so basically just one run, then you're already done. Sometimes two, in a very worst case, three. On paper, it can of course take much longer, but this does not happen. Okay, so not optimal anymore. Only step 2 is optimal, but it's very good, as we will see. Okay, so now we know both how to score a summary, we know how to find a good cover, and well, finally, we need to find a good pattern set. How do we do that? Basic idea, I'm going to reiterate, and now I have colorful boxes to explain it. This is the same idea that we use in Crimp, or actually in Slim, not in Crimp. Used in Slim, but also in Grab. We exploit patterns in how the data is encoded currently. We see if there are patterns left, because if there's patterns left, that means there's redundancy. Redundancy means that we're wasting bits. By removing the redundancy, we gain bits. We're doing compression, so that makes sense. The moment we can find a pattern in the code stream, that means that there's structure that's unmodeled. That's what we want to grab by its tail. So we start very simply by encoding the data using the initial code table, just a singleton only code table, which is this one. And now we try to find patterns there, given some maximum minimal window length, right? And doing this in a smart way, using every individual symbol as a potential starting point. So every like potential symbol, I mean in the alphabet way, right? So we A, what are then the patterns, and so on and so forth. And what we then see, A is very often, or remarkably often, followed by B. Let's add it to the code table. And then lo and behold, we actually gain some bits. Okay, so now we have this one right after the whole optimization that we had in step 2. We now look further. Hey, well, C and D, they seem to share some behavior. We find C and D, we call it pattern Q, and there we are, right? For this sample, just done. So effectively what we're doing, given a code stream, generate all code pairs. You can also do triplets, quadruplets, and whatnot, but hey, wasting CPU time is something I like not on every day of the week. We consider those as candidates. A lot of them we can already throw out because we can estimate, just like in Grab, like if they're going to be any help or not. Those, if they're not help, we don't even look at them. And every moment that we change our code table, we accept a candidate, and we add AB, then we should, of course, regenerate the candidates, regenerate all the statistics, and there we are. That is very costly. So just to shave off some computation time, we actually generate a batch of candidates, so AB, AC, and so on and so forth, right? We add them until that batch is empty, and only then we generate a new batch. It's rather greedy, but it saves the day. Put it in a picture, it looks like, well, very similar like Slim, and I use the same template. This is how it then works in practice. So the orange one, well, it works slightly, actually higher is better. Higher is more bits gained. I had a huge discussion with my co-author back in the day, Nicolai Tatti, that in my case, I mean, in my brain, if you want to do compression, you should go lower. Lower is better, but they're like, no, higher gain is better. And in the end, we decided, okay, let's have a beer and let's never speak about it again. So I could just rant to you guys about it. The orange one is actually a slightly different algorithm, a bit more naive, but it does not have this batch behavior. The purple one is the one that I just described. So you can interpret the orange one as the slow one, right? The performance of the slow one. And the purple one is the behavior of the fast batch waste one. And as you see, they arrive at essentially the same optimum. Slightly different because local minima and whatnot, but that's all fine. Good. Does this work? We mentioned earlier, and I'm just going to drive it home further and further. Whenever you propose a new algorithm, try it on random data. See if it does anything, right? So to bash again on my favorite topic, I mean, in this whole deep learning and it's massive overfitting, double dip type of behavior, the fact that you can learn with a sufficiently rich neural network, even the labels after you permuted them completely randomly, right? You take ImageNet, you have God knows how many pictures, and well, I don't know how many labels, I mean, hundreds, thousands of different labels. You now permute them completely randomly, right? There is no match anymore. You can still get very, very high accuracies. It's something that on the one hand is amazing, at the same time it's very, very scary, right? These things can learn essentially anything. If this is good or bad, well, perhaps a discussion for another day. In this particular case, I want to gain insight in the data. So if there's no structure, I want to see no structure. Exactly what it does. If I generate data with a hidden Markov model, so I have a probabilistic model where I really say, okay, well, after generating an A, I have a much increased probability of generating a B, and so on and so forth. What do we find? We find exactly those paths. Very good. Also good. Now, how do we evaluate this? I could have ran it, of course, on the alarms data set or on the train delays data set, right? And then, yeah, you find something, but you kind of need to believe me that, look, yeah, it's really a pattern that alarm A, B, and C, and the expert said so. Tons of papers do that. We're also partially guilty now and then of this game. But you as the reader, like, yeah, whatever, right? I mean, maybe, I don't know. I can't really say. So what we typically do with sequence mining, we go for text, even though I'm not an NLP person and I refuse to become one. But text does allow me as a human to read whether these sequences of words make sense, right? If these capture concepts and actual patterns. I'll show you some examples that you partially have already seen in a minute. And then we're going to build upon that afterwards, because so far this is all old hat. And this is, we're not, so the first part with the pattern mining is like late 90s. Now we're in 2012, right? And we're slowly moving towards now. And that's, I promise you that. So does this work? Yes, we go from, these are a database of presidential addresses. These are abstracts from Journal of Machine Learning Research. This is the novel Moby Dick. What is the alphabet size? Well, large alphabets. How many sequences are there? Well, many. How many frequent episodes do you find? Well, thousands. And basically, this is with relatively high frequency constraints. So this is basically the old school methods, useless. These are the number of patterns that Squeeze finds. Squeeze is the name of the algorithm. And this is the number of bits that it gains. Well, great, hundreds, fine. Are we really convinced? Hopefully not. It finds reasonable things. J. Millar, I mean, these are indeed the major topics of the time, the presidential addresses. Yeah, of course, there's Army, Navy. I mean, they take an oath because that's what they do. And under difficult, under different, and so on, other circumstances, everything would be different. That is fine. Let's move forward in time, because this was 2012. When I wrote this paper, I was still in Antwerp. 2013, I moved here to Saarbrücken. And in early 2016, late 2015, early 2016, I started working with Apratim Bhattacharya, so master student, or at first he started as a Hiwi, and then became a master student. Currently, he's a postdoc in Tübingen. And we said, okay, well, Squeeze is nice, but tja, right? To put it in proper German, tja. It is quite limited. Can we improve it? Because there's a lot of things that we don't like about it, or that you can very easily say, okay, well, that is something you would want in a sequence analysis method. For example, the pattern language, serial episodes, I mean, allowing for gaps is already nicer than just having subsequences. I mean, I hope you agree with that. But this can also happen, right? So the bottom two that I just show, I mean, they share the starting and the end. And in the middle, yeah, it's a B or a D. Suppose that we have such a pattern, A, B, or D, C. Squeeze would just find two patterns. Suppose that there's more elements in the OR, it would just find the whole abundance of, or actually it would not find any of those because it would just find AC, because what the hell is happening here in the middle? We lack expressivity. So this is what we want to find. And well, in the big book of say episodes, named episodes, you have serial episodes, you have parallel episodes. This you don't have. So we need to come up with a name. And in this lecture, I call it a choice episode. When I talk to any of my students, it's a choice-isode. Right? So I'm now from now on also going to call it a choice-isode here. But it would be cool if we could find this. This can also happen. We have the ABC, and another instance, ABCD. Well, what is this? I mean, this is essentially ABCD or stop. Well, if that one is a choice-isode, that is a stop-isode. Obviously, right? But, with enhancements like this, you can, especially when the data is noisy, which it will, right? You can actually capture much more the gist of it. You're going more towards mining concepts rather than just token patterns. Well, moving from tokens to concepts is something that we're still venturing into. Difficult, but cool stuff. So this was originally Apratim's master thesis, and in the end we published this, or in the end, I mean, just a few months later. The other part, Squeeze, that we didn't like, is the type of cover that it allows. So here we have some data. Squeeze, well, non-overlapping. So if an A, B, C, I mean, if it uses the ABC, those ABCs cannot be used for any other pattern, and sometimes you may want that. Non-nested. So if we have AB, and maybe there is a perfect, what is it, CD here in the middle, no, we don't allow that, right? This was our little secret. It sounds a bit horrible, but okay. I didn't tell you why, actually. I will tell you why after I finish this. And we don't allow interleaving. So A starts, then, well, so basically A, B, and then C, D. It would also be nice, right? So slightly more expressive form of nesting. Where can I'm trying to find a good slide where to show what. Yeah, I think here. So why don't we allow patterns inside of patterns? Or why do we encode the gaps only with singletons, even though the encoding technically allows for patterns, right? That was essentially what I said earlier. So when we do encode, let me actually go even further, because yeah, if I do have a slide for this, it's essentially here, right? Yeah, it's a gap, right? Oh, we're going to read something from the pattern stream. And what I said is that it could, in theory, this definition allows for any, but the way that we do it in practice in the algorithm, only singletons are allowed. What this comes down to is that I'm using suboptimal codes effectively, right? I'm encoding, hey, it's going to be a D, including the option it could have been a P, even though we know it couldn't. I'm wasting bits. So when back in the day I presented this for an audience in an information theory conference, and I explained this, and for them, oh, cool, because they're very in the theory side, it's more practical. I mean, that's actually their theory actually becomes useful. And they said, yeah, well, we consciously make a suboptimal choice here. And there was literally in the room like, ooh. It's the first time I had really like this strong disapproval from the, ooh. There was a good reason why we did this. It's a good reason why we have this secret. Because when we started, we were smarter, you could say, and we did not allow patterns in gaps, also in the encoding. So if we saw a gap, we only looked at the usages of singletons, or even usages of singletons in gaps. So that's really like a noise element. And the problem is that it worked too well. And the algorithm got really happy about this. And essentially what it now started to find were patterns, like sometimes a B, a CD, whatever. But whenever there was a stretch of nothing, right, just mean random noise, what it would find is a pattern, whatever the symbol was at the beginning of this stretch of desert, and the element at the end, because here in the middle, all of a sudden, it did not have to say, well, this is just an A, just a B. No, no patterns can happen. It could save bits by identifying here be nothing, here be dragons, which is great, right? In a way, it's nice and expressive, but yeah, not really what we wanted, especially given that patterns are often relatively sparse in data. And for certain data sets, it just found, okay, first symbol, last symbol, done. Yeah. And in this algorithm, we did not have a way to get this algorithm, oh, whoops, yeah, so the dynamic programming algorithm to actually work efficiently well, or even at all, allowing this nesting and interleaving. So like, okay, well, you know what? We're just going to play pretend it's just singletons, right? But we don't tell the algorithm. Oh, yeah. I had a long discussion afterwards, and they were really like in this cognitive dissonance state, right? Like, yeah, I see why you do it, but you should not do it. But if you do it, let's see if we can do this better. Yeah, okay, but was lovely, was lovely. Okay, good. Back to Squish, back to 2016. Where were we? Yeah. So non-overlapping, non-nested, non-interleaving. In the new algorithm, we allow, first of all, nesting. Nesting, if you think about it, is already quite easy. If I allow within the context of, let's say, pattern P, I say there's a gap, and now you read pattern Q. Well, if that now means that we first have to finish pattern Q, and after we're done with pattern Q, then we continue finishing pattern P, it's easy peasy, right? The context of which code you can find, it's just nesting, easy peasy. We could have even like P and then Q and then R and then S and then T and U, all fine. But the moment they start to interleave, that becomes a little bit more tricky. So, however, Squish can also do interleaving. It's just in the end turned out to be a slight reformulation of how do you count, how often does a gap or a fill code, in what context may it appear, and it made the code slightly less efficient. Like we waste more bits in individual cases, but overall it becomes better. So it was nice. Overlapping, we didn't solve. That's still an open issue. It's not just better covers. On this slide, I didn't include it. It's also faster covers. Because rather than using this dynamic programming approach, essentially what we do in Squish, greedy. We look at a stretch of data, and the first most used pattern that fits, we use it, and so on and so forth. And then there is a slight optimization phase, but greedy works absolutely fine there. In fact, it works better if you look at the final results than the optimal, it is optimal, but I say between quotes because of the iteration, dynamic programming approach. So when I showed it to Nikolai, and co-author of the first paper, he was like, because he's really like the algorithmician. He's like, damn it, yes, yes, it's nice, but I don't like it. Yeah, well, too bad, I do. Because it's really one of those cases of harder, better, faster. The problem is harder. We have more expressive patterns. We get better results, and also happens to be faster almost always. So here we have squeeze. Here we have squish, allowing for interleaving. And as you can see, 5 minutes, 3.9 seconds, 8 minutes, 6.5, and so on and so forth. The gains are also higher, right? There's a number of bits, and essentially, as you know, as long as you have a few bits gain, more than 5, more than 10, you have a better model, right? 10 bits gain corresponds to a p-value of 0.001 under certain assumptions, but let's not go into details there. Yeah, okay, well, that is nice. Choice episodes, same thing. Good. Let me give you some examples. The serial episodes you already know. So and for the presidential addresses, we again still have the Army, Navy, United States, take oath, and so on, right? This is the old school stuff. What type of choice episodes do we find? Is there anything sensible there? Is this just a nice idea on paper? Or, as I like to call it, I mean, ideas that are nice on paper but completely useless. I like to call them academic masturbation. You write a paper, but then, who cares? I mean, you should just do it in your own office, and that's there. Good. Okay. Maybe I cut this from the video. Let's look at the choice episodes that Squish finds. This is for the Journal of Machine Learning Research. Well, you are somewhat experts on the topic already. I mean, risk minimization. Which variants do you know? Empirical risk minimization, structural risk minimization. Makes sense, right? This is the same concept, the same pattern, just slightly different. Independent, respectively, principal component analysis. Yeah. You could have two specific patterns, but this is the same idea. Different types of distances, Mahalanobis, edit, Euclidean, pairwise distance, the concept distances, right? And I'm not saying that these words, that independent component analysis and principal component analysis are the same thing, but as a concept, when you read an abstract, yeah, this can now pick it up, this is cool. And so this was the master thesis originally of Apartim. This is the master thesis of, back in the day, Kathrin Grosse, who also then did a PhD. She did it here at CISPA with Michiel Bakkes. She's now a postdoc in Padua, or somewhere in Italy. I'm not sure if it's Padua, actually. And with her, since she was a linguist, we looked at ontological episodes. So different than what Squish does, right? But basically, we allow generalized symbols. So we can find in text data patterns of the type he, verb, conj, he. For example, he said that he, or like and this is a wildcard. This is a gap essentially. I forgot what does conf stand for again in this. I'm really not a linguist. I used to know. I know what a noun is. I know what an adjective is. Is it a confluence? I don't know. Well, it corresponds to and, whatever an and is. And the noun of, the end of, and the end of. That, which these patterns are more expressive. They capture much more, right? I mean, it's not just the nitty gritty at the service level, the token level. It goes more towards, well, giving some glimpse of this is how language works. I'm not saying this is the ultimate toward language modeling, by far no. But you know, the adjective noun and, I mean, the young hobbits and, yeah, this is a building block, right? I mean, that you could not find just by looking at service level, not by just looking at n-grams and so on and so forth. So this was Kathrin's thesis back in 2016. Well, enough about 2016, right? I mean, let's go to, well, not to today, literally. I mean, not. I could have presented Josha's work that we're just writing up right now, but let's not. Let's go to 2020, which was his first paper. But I propose we do this after the break, because we've already been talking for an hour, I now realize. And I want some fresh air. So let's take a 15-minute break. Unless everybody votes for 10. Who votes for 10?
That's because I have to.
Okay, 10 minutes is this. 10 minutes it is. Yeah. It is because. Okay, good. 10 minutes it is. So this lecture, I'm not going to. Yeah. Absolutely. I have the feeling I'm forgetting something, but slides are ready. Audio seems to work. Oh, good. Then let's get going again. So, what have you been doing? Well, essentially right now in the last hour, I've been showing you how you can essentially transfer this idea of pattern mining from tabular data to sequential data. Just to summarize two main messages, you can have much more expressive patterns on more structured data. And all of a sudden, simple things like just simply counting become difficult, right? with the minimal window stuff, we can in a single sequence easily find, or relatively easily still count, does AB happen as a pattern? But yeah, now think of, let's say, a graph. Suppose that we have a labeled graph, right? So nodes are labeled. And now we want to find graph patterns. If you have many graphs, counting is easy. Just find it in a graph and you're done. But how frequent is a pattern in a graph? I'm not going to show you today, but structure, it makes certain things possible, makes certain things very difficult. And well, I like this game of getting closer to the data generating model. Everything we've seen so far has been purely unsupervised. Just summarizing. I mean, given that almost all of machine learning is focused on prediction, I mean, the summarization game is the one where there's very little expertise. And you now know very well, or much better than almost anybody, what is possible and to a certain extent what is not. Subgroup discovery, sort of a weird in between, right? It is unsupervised, supervised, exploratory. It's a little bit of everything. Now, I like these sort of weird problems, as may be clear by now. And in sequence land, there are a lot of methods aimed at prediction. So, for example, even like well, BERT, GPT-3, whatnot, right? Essentially, a language model, essentially predict the next token. That's what they do, right? Sequence prediction. Tons of methods exist. Most of them completely black boxes. I'm not so interested in them, to be precise, to be honest. There's lots of methods that do sequence classification. If I give you now a sequence of a particular length, A, B, C, D, E, F, G, is this now a label 1 or 0? Something like this, right? Is this a bad or a good sequence? Also, it's not that interesting. I mean, you can undoubtedly map many problems to such a setting. It's not really what makes my heart go beat faster. Project I'm going to describe right now, in the next half hour or so, got kicked off in, I think, late 2019 when I had a chat with Jens Dittrich, so lecturer of big data engineering, right? Yeah. And basically, it came to the topic of earthquakes. And you're like, okay, well, can we predict earthquakes? Like, well, in general, I don't think so, because from all we know, right, all the sensors, I mean, it's extremely difficult. But in theory, why not, right? If there is any type of pattern, we should be able to detect this. And then, well, discussion, whatever, whether we went deeper or sipped more coffee, I don't remember. But the thought kept brewing in my brain. And then with one of my then master students, Josja Kuppers, currently PhD student, we started working on this for his master thesis. And what and very quite soon after, we forgot about the earthquakes themselves, right? Because getting the data and getting discrete graph, and too many questions that we don't want to answer right now. But this general idea of predicting, finding those signals that lead to a reliable prediction, because most of these existing methods, they essentially tell you if they can find such a pattern, like something is going to happen. And then when? In the future. Could be now, could be next week, could be in a year. I don't know. And that didn't really, I don't find this that fulfilling, right? It's a bit like, well, if you tell me like, oh my God, be careful, there's an earthquake coming, I would like that to come with, well, within the next 3 days, or in 3 days, that you basically know what to prepare for. And rather not like, well, in 5 seconds, rather with a bit longer delay, right? So that changes, of course, the game of what type of pattern you're interested in. What is the setup? Setup is we have an event sequence, currently just one, right? Yes, it could be multiple. It could even be continuous valued, and you can do discretization on it, right? You can do on the fly, whatever. So, but discrete, in the end, all data in a computer is discrete anyway. This is what this looks like. And in addition, we're now given another event sequence, but it's just a binary sequence, just zeros and ones. Right? We call it Y. This is the target sequence. Right? So we're going a little bit more into the supervised domain. And 0 means meh, boring. 1 means, oh my God, interesting. Interesting event, interesting time point. As you can see, in this Y, there's a bunch of these ones, right? But this could correspond to an earthquake. could be something else, right? We just indicated like some moment in time that we would like to predict for whatever reason. Now, in this data, you have, for example, pattern CE. And pattern CE predicts the number of the ones in Y quite well. Is CE a good pattern? Given that I already gave you the motivation, I hope that you say, not really. If we look at what we call the delay distribution, the distribution from the pattern occurring to the event happening, in half of the cases, in 2 out of 4, but okay, it's 1 time step from now, and 5 time steps or 8 time steps. Yeah, something is going to happen somewhere in the future. Not really my favorite pattern. The same data, we also have pattern AB, and AB predicts as it happens exactly the same events, but super reliably. When you see AB happening, you know in 3 time steps from now, shit is on, right? Of course, if you're specifically interested in long distance, then maybe this one is then good, but this is something that I call actionable, right? Interpretable, reliable, actionable, just a bit like in subgroup discovery. The question is now, how can we find these ABs rather than the CEs? But before we go into that, I of course need to make it a pattern set mining method, right? Because hey, that's the name of the game. And you should already remark that there's a few ones that are unexplained, because why do I want to make it a pattern set mining approach? Why am I not just satisfied with just AB, the one pattern to rule them all? I do not believe that our modeling language, these patterns, is, well, is a match for the complexity of reality, right? Truth is stranger than fiction. So in this case, same thing. So we have then AB, but those ones are unexplained. And actually, we can explain them very well with another pattern. So rather than saying all interesting events are caused, originally this project had a very causal viewpoint. We ditched that, but could make a very nice bachelor thesis, for example, to connect this to some real causal theory and to improve the method. But if we do cause between quotes, there can be different mechanisms that lead to a 1 in Y, right? Can be 1, can be multiple. Who knows beforehand? So what we want to find is a set of patterns. Each pattern comes with a delay distribution. So how long do we need to wait until we see an interesting event? And overall, we want this pattern set to provide reliable, actionable predictions. MDL, blah, blah. I'm skipping, I've removed the slides, right? I mean, I can only show them so often within one lecture. What do we have here? We have pattern EF and we have pattern AB. Both are good patterns, right? Essentially, what it comes down to is that the cost of the model is a sum for all the patterns. This is the cost of a pattern. And a pattern is essentially the cost of this here. We're not looking at the histograms just yet. Let's dive in. So here we have 2 different patterns because I needed to create a bit of why is AB better than CE, right? Because that's what we want the method to do. Because that's the intuition. How we encode this, and these are all choices, right? And these choices, they need to match our intuition. What do we want to find? Like we don't just take a distribution from the shelf. In our case, we like the right-hand histogram better because it's more peaked. The more peaked the histogram, the more reliable, more predictable. Essentially, the lower the entropy of a distribution, the more I like it. The left one is almost flat, right? Almost maximum entropy. The right one, almost, or actually not almost, minimum entropy. So that's great. Essentially, we encode this by the entropy of the distribution. Again, I'm going to skip the nitty-gritty mathematical details. I mean, you can download the paper. I mean, it's not part of an assignment so far, but Tim has a question.
Not really a question, but
more of a comment.
You uploaded,
yeah.
All of the boxes are essentially covering interesting parts, and maybe you can
I will. Yeah, it's been so it's in this part of the presentation, right? Previously, it should have been fun. Yeah. So in this part, yeah. So this, I'm using Josja's slides here, but we developed it together, and I like animations and I like graphical design, and Josja likes this even more. And I'm a little bit more experienced with lecturing, so I typically unroll these things, and yeah. There are a few edits I wanted to make to the slides, and then I looked at them at this giant stack, like, no, I don't need to make this change after all. So. Good. Okay, so now we know how to basically how a good pattern costs fewer bits than a bad pattern. That's a longer pattern more than a shorter pattern. So that intuition is covered. How do we now encode the data? So it's different than what we did in squeeze and squish. The first thing that you should realize, we are not interested at all anymore in encoding X. That was the goal of the whole name of the game in the first half of the lecture. Right now, I couldn't care less. X for me is just a tool, right? To see if a pattern, let's say AB, when it happens, and that just essentially the flag goes up. That's all I want, right? It's just a condition that hits. I'm not going to encode X. I'm just interested in the length in bits of Y given X and M. Okay, so how does this then work? Well, we have X and we have a certain pattern. Let's say AB. Like I mentioned, I'm interested when a flag goes up. Z is essentially this flag, right? So the moment we see A and B, right? So not already at the A, because we need to be able, we can only react the moment we saw the entire pattern. We don't want to spook everybody like duck. Oh, no, it's fine. Duck. No, it's only duck and cover when you're supposed to. Okay, so that is essentially, this sequence is what we're going to be working with from now on. And this is the one that we want to predict, that we want to map to. But as you can see, there's a bit of a distance in between, doesn't match that well. But what we're going to be doing is we're going to try to map each of the instances of a pattern to an instance of an interesting event in the target. And we're going to try to be doing that in such a way that we minimize the entropy of this delay distribution, because that's the cheapest one, right? We could match it everywhere, but we don't want to do that. In this particular case, the nearest mapping of this pattern occurrence is then 1 times the beyond. We're only interested in patterns that predict at least 1 time step ahead. Like instantaneous effects, we're not interested in, right? I mean, like saying AB is a pattern for an earthquake occurring. Yeah, okay, it's a little bit too late, right? I mean, that's you should have duck and cover. Felix.
Previously something happened.
Yes, that absolutely. Yeah, this is in this case not what we're interested in, but exactly, you could do it exactly that way. Yes. Although, no, actually not although. It's actually very interesting. Like, what are the effects of of things that happened in Y? Yes, but absolutely. I mean, okay, now I need to be a little bit careful. It almost seems that if we now just inverse the sequences, then it probably should already work. But I'm not 100% certain if I'm not overlooking some a very important detail, right? So let's park it as an interesting part. Good. Well, okay, this one maps with +1. This maps with +2. Here, this one doesn't map to anything. This maps like either immediately or right? So this one we want to skip this prediction. It's the first time I tell you about the symbol. So in the histograms that we just saw, I only showed you the delays to actual predictions. There's actually a secret column, let's say the 0 delay column, we don't use it anyway, right? Which are the skips. And of course, well, the more skips you have, the lower the entropy of the distribution, but yeah, then you also don't predict anything, so you don't gain any bits on Y. So that is in the end where sort of the balance is struck. So in this particular case, by setting these delays as follows, we can explain in this our approximation of Y, hence Y hat, explain this real Y, this one Y, and this one. Which means that those we do not explain, right? So that would mean that if we now would have a model that only includes pattern AB, we do not reconstruct Y without loss. And MDL, the name of the game, is lossless. I'm not sure, actually, I don't even think that I mentioned why this is the case. Just to allow me to do so. The moment you would go to a lossy version of MDL, then you would allow through the back door essentially the model that doesn't explain anything, which, well, is very cheap, right? And it doesn't explain anything. And okay, this is fine, right? That one is going to beat, well, the model that does explain everything. And how do you now, and that's perhaps a bit too extreme. So like, yeah, okay, but if it explains 95%, okay, but which 95% of the data? And only if you encode lossless, then you know that every model that encodes lossless, well, they encode exactly the same thing. And out of those, you can select then the one that is most succinct. Right? The moment you allow any lossiness, you lose your control over what is it explaining. So you might then have two models, one that is a bit lazy and explains the general gist, and the other one, well, really focuses on the important parts of the data. Yeah, which 5% did it now throw out? You don't know beforehand, hence lossless. So we need to make it lossless too. And what we do, well, between these two sequences, we can simply take an XOR, right? Those are those elements that we did not explain or well, overly explain, but that we don't allow here. This we call the residual. That's exactly what it is. And if we now encode this residual, essentially just by entropy, so what is the probability of seeing a 1, right? That's the code for well, the negative logarithm of that. That's going to be the cost for a 1. Same thing for the zeros. The more zeros we have, the happier we are. That's essentially the idea of the encoding for the residual. And the encoding of y hat, what is that? That is not the entropy of this thing here. No, that is because we find where the ABs, where the pattern is happening in X. So what we need to encode are essentially this A here, these delays. That's all we need to encode. And that we use using our histogram. And as you know, a histogram is just a probability mass function. Just gives us probabilities. We take a negative logarithm for these probabilities respectively. There we have it. We have the entire encoding. Looks like this. Okay, just like in squeeze and squish, that is then the way how we can approximately score how good a model is. We still need to find good covers and then also good patterns. The name, the game remains the same in that sense. So how do we find a good alignment? If I give you this Z, so I remove the X, right, just not to clutter the slide too much. This is why, I mean, how do I find a good alignment? There are many, many possible alignments. Finding the optimal one, I mean, good luck, right? I mean, that's good luck in wasting your CPU cycles. We need something that is fast. The heuristic we use, or we propose two, depending on if you have long or short-term dependencies, but the short-range dependency one essentially maps every occurrence of a pattern to the nearest interesting event in Y. That's this. And we automatically, of course, then get our delay distribution, right? Where here now, as you have this column for the skip, essentially the 0 column. We also see that hey, both of these now predict the same thing. We don't want that. That would lead to, well, again, a bit like in squeeze, these weird type of models. We don't want this. Let's get rid of them. So what we now do is we identify those that have two incoming edges. We don't want that. We remove the one that improves the call it, or gives us the least increase in bits if we remove it. Well, whoops. So that is what we do. We remove it. We make it a skip in this particular case. And what we now do next with the new, now updated delay distribution, we see what would actually be the best thing to do with this one, because we can make it a skip, maybe something else. And actually, it turns out that if we now map it to the one further, it fits our distribution remarkably well. Okay, but now we again have a clash. So we remove that one, we remap it, and so on and so forth. We can do this in one sweep very efficiently. And as you see, we went now from a distribution that was mostly meh to something that is perfect. It's a beautiful pattern, right? Very simple optimization scheme. Of course, in practice, you're almost never going to get this single peak, right? But in the overall idea, making it peaky, that works really, really well. How do we now find pattern sets? I should actually give also one other small caveat. I mean, what is a pattern here? Because you might still be thinking about serial episodes. That would be good, except it would not be correct. In this project, because we're really focusing on these delay distributions, we didn't want to bother with mining serial episodes and minimal windows. So it's just subsequences. We really like a pattern. It's just like ABC really means we need to see ABC. It's not like A blah blah BC. No, it's very easy to extend it. It's like, I don't know, what is below a bachelor's thesis, right? I mean, that's something like that. It's like, it's not a heavy project, not in my group, but okay, this is like a a quick project just for the heck of it. Good. Now let's find pattern sets. The naive approach I actually should have removed, I should have animated this one. And I should say, well, let's start with all the singletons. And you would like, yeah, okay, we go again, right? And then we find the pairs and yeah. Nope, it doesn't work. Sadly, or luckily, depending on how you look at it, right? Problem is that all non-compressing patterns, they will have exactly the same length in bits. I see you frowning. I can give an example a bit later, like on the board perhaps. But essentially, MDL gets stuck almost immediately. Basically, you stay stuck with the singletons. It's never going to find actual patterns. And yeah, that is kind of meh, of course. So what we do, and what is the problem? So we get stuck, right? So we have A and we would like to find ABC, but yeah, AB is not going to be better than A or much better, right? And only if we have ABC, then it's all of a sudden good. You see this all the time in this problem setting. So you really need to somehow look ahead. In the previous settings, we could just happily grow from a simple pattern to a more and more complicated one. Everything was fine and dandy. Here, no. So what we came up with is an idea where we use an optimistic estimator. So again, a bit similar to the line of research in subgroup discovery. Essentially, what we do is that we have now a pattern A, and we are looking to expand it into A, B, A, C, whatever, right? We're not, and what we now look is, we have a number of instances of A. Let's say there's 10 instances of A, right? And currently, not all of them map perfectly to an interesting event. And that's why we want to refine it. So suppose that we can now magically get rid of the bad instances of A, such that the ones that we have left map as perfectly as possible to interesting events. That would be nice, right? Well, that is something we can actually relatively easily do, because just imagining that A is not there corresponds to imagining that the good instances are not just A, but actually are AB. And the bad instances are not AB. So the moment we would grow from A to AB, or if we're now at AB and there's still one or two bad instances, we can imagine, hey, well, maybe by adding a C or a D or whatever, we can essentially measure how good would be the perfect instance, the perfect, let's say, optimization, the perfect extension, not knowing what this extension is, right, of this pattern, what would it score? And that we use, and then we can do a tree search over this, basically a lattice-based search, and that works. So we're not going to be simply just combining two okay patterns into increasingly better patterns. That doesn't work. We really need to look ahead, and well, this allows that. So what is the algorithm? We start with an empty code table. Then an empty, as always, includes the singletons. We do this pattern search, where we look what is the best possible expansion of A, respectively B, and so on and so forth. Do note that the extension of this to serial episodes perhaps is more of a bachelor's thesis than I thought. Perhaps it even becomes a master's thesis, I don't know. Because this part over here, this optimistic estimator, now that I think of it, is not going to be that trivial to extend in a computationally efficient way and statistically reliably. So here we really leverage the fact that we're looking at these simple subsequences. Okay, so we search for good patterns. That generates us candidates, right? I mean, we think that AB is extendable to something useful. We think that AC is, and so on. That's the pile. We take the best estimated one. We put it into our model. We check if MDL likes it. We rotate, and well, that's essentially the algorithm. The algorithm is called Omen. It used to be Cake. Cake was the original name in the master thesis because it was for causal patterns. Yeah, so what was the title? How to make cake. Discovering causal. I forgot what the K stood for, but anyway, it was a good name. But then we brought it up as an actual paper, and that after refining it, and I think Omen is better, right? And that, and Nomen is the Omen, so that too. Good. Does it work? Well, let's start by some data where nothing is happening. Huh? What we're going to be doing. So if nothing is happening, actually, it works. That actually I don't even show. Can we shift? Let's start by evaluating whether the score works. So if I give you the right pattern, can you say like, this is a good pattern, yes or no, right? And we have this fancy MDL score that we just conjured up, right? I mean, and maybe you don't trust us, maybe you do. This score essentially says something, is AB a good potential cause for an interesting event? That's essentially what we're looking for, right? TEND is transfer entropy. It's an established method for establishing causal dependencies in discrete data. QT is a method that I developed together with Kailash Budatoki, former PhD student of mine a few years ago, which basically can tell whether Y causes X or X causes Y. And if you now use it, well, just in the one direction, then actually it also behaves this way. Let me first show what we're now doing. We have a sequence in which we plant in X 50 predictive patterns, which associated ones in Y, 25 just frequent patterns that don't predict anything in Y, right? Just to confuse whoever is looking at this data. Then we have on the left-hand plot, we remove some of the true ones. So some of the predictive patterns all of a sudden are not so predictive anymore, right? In the right-hand plot, we add ones. Basically, there's interesting events that cannot be explained. Okay, so now how does this work? Qt and TEND, well, they basically do just nonsense. Then if we give Qt and TEND let's say the machinery behind Omen, this refinement machinery, actually, where are we? I don't know where the dashed lines are. They should be somewhere in between, but it's not good. Anyway, let's forget about the combination of the two. This is what Omen does. Yeah, I mean, so this is just the beginning of the story. I mean, so it actually works quite well with high percentage of noise. Okay, then the accuracy starts to become, I don't know if this is now good or bad, but for lower noise or lower, I mean, up to 60%, which is ridiculously high. If we now plug this into a search, well, we have Omen, and essentially all algorithms that exist do some of these other games, like what is the next symbol? I mean, what is the label? So we once again came up with a problem that nobody has really tackled, even though I like to think this is a good problem. This is a real problem. So it was a bit tricky to come up with a good competitor set. Squeeze, you know, we could have also picked Squish, I mean, basically same result. Squeeze just summarizes X. Well, now, if you take the assumption that good predictive patterns are also frequent in X, then by first summarizing X and then filtering out those patterns in X that you found that are not predictive for Y, you would have the poor person's version of Omen, right? That's essentially what Squeeze plus Omen is. So we use the Omen score to filter out the bad patterns that Squeeze found. SCIS is a sequence classification scheme that's based on patterns. And essentially what we ask it to do, we give it all of the ones in Y, and what it's supposed to do is find patterns leading up to that Y, not bothering with delay distributions and stuff. This is it. And as you can see, destructive noise, well, Omen does well, the others are a bit meh. For additive noise, the F1 goes down really quickly around here. Let's investigate this in a second. But first, let's look at if we now combine these two noise types. No, doesn't make it better. No surprise there, right? If the additive noise is already quite horrible, if you both remove and add stuff, this looks bad, but is it? Right? Sometimes you have also in papers, they report let's say an F1 score of 0.4. Yeah, well, we all know that 1 would be better, but how difficult is 0.4? Most papers don't even bother to investigate this, which is a bit strange because, how difficult is the task, right? But in this particular case, we can evaluate this because this is all synthetic data. So what we can now do, we can actually look for each of these data sets. We can see what is now the compressed size of the null model? Null model being there are no patterns. The target sequence Y is just generated completely at random. It's essentially just encoded by its entropy, right? That is a valid encoding. As you can, this is this line over here. Then the planted model is like the true model. So how we, and you see, okay, this takes in this case way fewer bits, and then it starts to climb. And at one moment, the planted model is actually worse than the null model because of all the noise, right? So we planted it, but then we destroyed it. So it's a bit like picking the Mona Lisa and then spraying like lots of paint. Yes, it's still a Mona Lisa, but not really, right? I mean, is it now worth something? Is it more, less? I don't know, depends who sprayed the paint, I guess. So what do we now discover? As you can see, the orange line, well, it's not quite on top of the green line. So there's some room for improvement, but it follows the green line up till here very well. And over here, yeah, then it decides, okay, no, this is no structure. I'm not going to overfit. So the fact that this drop-off happens is actually a good thing rather than a bad thing. Had it stayed up, it would actually be overfitting. So just to illustrate that sometimes a bad F1 score is actually a good F1 score. And I'm not just saying this to pat ourselves on the back, right? This is our paper, but yeah, be always careful in how you judge, both positively and negatively. These were all previously with very simple delay distributions. This is an example with a slightly more complicated one, some Gaussian with a very wide variance and a very high mean. The black bars are the ground truth. The red bars are essentially the histogram that we retrieve. Fits quite nicely. We could have computed the KL divergence or something like that, but I mean, this fits very nicely. Does it also work in real world data? Well, we didn't consider earthquake data in the end, but we did consider data from the river Saar, actually from a whole bunch of rivers, from different stations along the river, and then for given over time, and then figuring, does the basically for each station, is the water level, let's say, is it normal, is it below, or is it above, and in different gradations? I mean, this data that were given to us. And obviously, you would kind of expect that if there is, let's say, a surge here, that a little bit later, the surge here happens, right? So, can we predict these types of surges? Answer is yes. And I mean, on what basis? What we predict is based on rain, on weather data. And indeed, if there's like big storms, then you get the pattern itself is not really like, oh my God, we now learned something about the world, but the method didn't know anything. So this is nice. There's this, I forgot her last name. Her first name is Sasha. Somebody in some artist in Paris who logs her complete life. Like everything she does at the resolution of 10, 15 minutes, something like this, everything she does, she writes down. And well, you can find patterns there. Just some examples. I mean, after you cook, so we can designate then one of these specific things that she does as interesting, and then we can find patterns that lead up to it reliably. And well, leading up to dinner is often cook, cleaning the kitchen, dinner, just as two very simple ones. We also find larger patterns, but these are the most intuitive. Speaking of larger patterns, this is what we found in ECG data, so electrocardiogram data. And what you see is that here there's a rest state, there is the pre-charge, and that is a prediction for the heartbeat. Heartbeat was then the interesting event. This is the normal one. We also found, I think, two further patterns, which are, let's say, aberrations. So basically like, well, bad heart rhythms, which, well, I don't show here because what do you know about ECGs? What do I know about ECGs? But just, well, this is both a longer pattern as well as a one that actually shows some insight in the data. Good. Okay, well, that is it. What I had to say today about sequential data and patterns on sequential data. So let me just quickly wrap up. Structured data allows for more expressive patterns, which makes many easy things much more difficult, which is a good thing, often, as long as you can solve them. Squeeze and squish for summarizing sequential data, complex problem, fast heuristics, and as we've seen, they extract good models directly from data. Omen doesn't do summarization so much. It's more like conditional summarization, you could say. Some call it prediction, whatever it is. Reliable temporal patterns. Again, complex problem, blah, blah, blah. That's it. Thank you very much. If there's any questions, I'm happy to answer them. And otherwise, I'll see you next week. So, Tim, is this on time?
Yes, perfect.
Perfect. Very good. Very good. Okay, that makes my day. That makes my day. Good. Actually, now that I have you still here, I'm also going to send this over email. But so the next 2 weeks, I know what I'm going to be talking about. I'm going to be talking about graphs. Then in 3 weeks, I have an audience chosen topic. That is something I started to do last year or 2 years back. Essentially, I'm asking you at this stage, so today, to have either a look at papers we published in recent years. You see this also in, so you have the TADA website, and you also the top right publications. It's the group website. You'll see it. Like, hey, wait a second, this is interesting, just by title, abstract, or the entire paper. Also, alternatively, if you're like, hey, wait a second, this or that is a topic I would like to hear more about, or would like to hear something about. So I can I can talk about causality for ages, right? I can talk more about patterns. I can talk about fairness. I can talk about tensors. Essentially, I'm asking you, what would be a topic that you would like to have a lecture on that fits TADA? No. I also love birds and butterflies, but I'm not going to lecture about them unless I can find a really good reason to. Yep, good. And then, well, just shoot me an email or let me know next week, because I need a little bit of time to prepare such a thing, of course. And depending on what I hear next week, I might then also offer a few topics like, okay, which ones would you prefer? And then we go from there. Yep, good. Okie doke. Then, well, class dismissed.